to do a quick recap of the last part that we're doing.
Yeah.
Mainly this eigenvalue, eigenvector, and then these two important results. First is the spectral, and second is SVD.
Perfect.
So the important distinction here is that spectral is for symmetric matrices, and SVD is for arbitrary matrices.
Yeah.
So this works for general. So let's also, I want to make a couple of comments quickly here. Remember we discussed something called this similar matrices. A and B are similar if A is P inverse BP.
Yes.
Yes. So this is basically the change of basis thing that we said, like if you try to express the same matrix in a different basis, then we get this. The one nice thing about eigenvalues and eigenvectors is that eigenvalues don't change under a change of basis.
Oh, cool. Okay.
Okay. So if a matrix, let's say, has an eigenvalue of 5, it doesn't matter what coordinate system you are choosing.
That I
Any coordinate system, that eigenvalue remains 5, because what it is saying is in one particular direction, it is stretching by a factor of 5.
there's
And
no
that stretching by a factor of 5 is like a coordinate independent concept.
yeah.
Okay, so some people like in pure math distinguish a lot between which concepts in linear algebra are coordinate dependent and which concepts are coordinate free. For example, if I say the first coordinate is value is 3, that's like very much dependent on how you define the coordinate system. But eigenvalues being a fundamental thing, like one way to say that it is a fundamental characteristic of the matrix itself is that they don't depend on the coordinate system.
Got it.
Okay, which is important for us because in linear regression, we will often do transformation of the matrices, and then we'll make some comments about, okay, if the eigenvalue is too small or something below a threshold, then something happens or something good, bad. And those comments are independent of how you have defined the transformation and all that.
Yes.
Okay,
Okay.
so that's
That's
something I
pretty,
wanted to mention.
that's
And then for symmetric matrices, the eigenvalues are all real, and eigenvectors can also be chosen to be real.
okay.
Let's
That
add,
I know we briefly mentioned imaginary numbers and
yes.
complex planes last time. I mean, does that even in those cases? I'm confused why this is important.
Uh, yeah.
Isn't it kind of obvious that it'll always be real?
So the question is, so when you think about eigenvalues, what we are saying is that, okay, so along a particular direction, it is stretching by this factor. But how do you find eigenvalues and vectors? We haven't discussed that, right?
Hmm. Right.
So let me quickly add a comment here. So finding eigenvalues and vectors. So the classical way of finding this is using this theorem called Cayley-Hamilton, which is basically saying is that if lambda is an eigenvalue and you have a corresponding eigenvector, then what we have is determinant of A minus
Lambda inverse or lambda
lambda I
yeah equals
is
0.
0.
I remember this
Yes,
formula,
you
yes.
remember this one, right? Now, if you expand the formula for determinant, this becomes a polynomial in lambda.
Hmm.
So that polynomial, as you know, like polynomials sometimes can have real roots, but they may not have real roots.
Right. Okay. 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 Got it. So
So
if you
this may
solve
not
for
have
it,
real root.
yeah, if you solve for it and you don't get a real root, then that is not an eigenvalue then.
Yes.
Got it.
No, if it's not a real root, then it's still an eigenvalue. It's not a real eigenvalue.
It's not a real eigenvalue. Okay.
Yes.
That's still possible though. That's okay.
Yes, that's still possible. So eigenvalues in general can be complex.
Yeah.
And then if eigenvalue is complex, the eigenvector is very likely to be complex.
Got it.
But for symmetric matrices, this is a nice result that eigenvalues are all real, and
Uh,
eigenvectors also you can choose to be real.
okay. Okay. I get what you're saying. The condition here is that the matrix has to be
Has to be
symmetric.
symmetric.
Then we
Okay.
get real. Okay.
Yes.
Got
So the spectral theorem we have written, this PED, P transpose, all these things can be expressed in terms of real numbers.
it.
We don't
Got it.
need complex numbers for this,
Got it.
which is a nice thing for us because like if you are coding, then real numbers you just represent in a Python code as double. Complex, you have to introduce the complex library or something.
Got it. Yes.
So, and like you have to maintain complex numbers, data structures at every step,
Got
which we don't have to do it here.
Okay.
Okay. And similarly, the singular values can be real or complex.
Singular values can be real or complex. Yes, because it's not a symmetric matrix also.
Yes, because it's not a symmetric matrix.
Yes.
Okay.
Yes.
Next, I thought I will, if we have time later at the very end, we'll do a quick proof of the singular valued stuff and explain like how it works around.
Okay.
But like we have the basic idea that we can express the matrix as P, D, Q transpose. Important thing to note is let's quickly pay attention to the size. So suppose A is, so in the symmetric matrix, the matrix has to be square, right? Otherwise, it cannot be symmetric.
Yes.
So which means this P, D, P transpose, all of these are square matrices, and all are, let's say, n cross n. So we don't pay much attention to the size.
Dimensions, right.
But for the general matrix, because it's rectangular, you have to know which of these matrix, like what type, so that the multiplication actually works.
Sizes, right, of each of them.
Yes.
Yes.
So typically I write my matrices as n cross P because the data matrices looks like that.
Okay.
So then P will be n cross P, and then D will be P cross P, and then Q will be
P cross N.
P cross P. No, P cross P.
P cross P. Okay.
Okay. So basically the P matrix, so if you imagine like your data is like 1,000 rows and only 5 columns, like a long thin matrix,
Yeah.
then your P will look exactly that shape. And then D and Q are basically 5 cross 5 small square matrices.
Okay. Got it.
Okay. The intuition here, like I want to stress this because like a lot of time in linear regressions, you have lots of data points, but very few like good features.
Right.
So if number of features is small, then explainability of the model is also limited by that number of features.
Right.
Because they can have only so many combinations that can happen.
Yes.
From those features.
Right. Yeah, your D and your Q matrix will be small then too. Yes.
Okay. So that's basically all I wanted to say. So let's move on to linear models.
Yes. Maybe my question here, Sujay, is
Yeah.
the entire topic of linear algebra now. How
Yes.
much have we covered in the last 2 classes? Have we covered all of linear algebra? Is this the entirety of linear algebra then? What other topics?
So there are 2-3 different aspects. One I haven't covered is quadratic forms, which is relevant for linear models a little bit, but I will cover if I need it. I won't cover otherwise.
Okay.
Like in interest of time. The second is there is a huge amount of computational linear algebra. Like how do you actually calculate the matrices? How
Right.
do you
The
calculate the
algorithms,
inverse?
the actual.
All the algorithms and stuff. So, and there are a lot of decompositions and stuff like that. So for example, every matrix can be written as L times Q. This is a nice result.
I've heard of what does the word decomposition mean?
So decomposition means I can write the matrix as product of simpler matrices.
Okay.
So for example, when you look at this one, PDP transpose, the D is diagonal in between.
Yeah.
And then P is orthogonal matrix. So orthogonal matrix is supposed to be easier to understand rather than an arbitrary matrix.
Yeah. Okay.
So in some sense, this decomposition helps us understand the symmetric matrix S slightly better.
Got it.
Similarly, here L times U, L is lower triangular.
Oh, so below the diagonal, I guess.
Yeah, below the diagonal. And U is orthogonal.
Got
Okay.
it. Okay.
Now, why is it interesting? Because suppose I am solving an equation AX equals B. Okay. So I will just write LUX equals B.
Yes.
And then what I can do is I can write let UX equals Y.
UX equals Y. Okay.
I'm introducing a new variable.
Okay.
Like I'm trying to do some algebra and try to find X.
Okay.
That's my purpose. So let's, this UX thing, I'm trying to write this as Y. Now, if you remember that U is orthogonal, so U transpose U is identity.
Yes.
So I can do U transpose UX is U transpose Y. Okay.
Yes.
So that means X equals U transpose
Y.
Y. Okay.
Yes.
So that means that if I can find Y, I can find X easily from this equation.
Okay.
Okay.
Yes.
So that then instead of solving for X, I will try to solve for Y.
Okay.
So now my original equation is now giving me Ly equals B.
Yes.
Okay. Now my claim is this equation is easier to solve than the equation Ax equals B.
Okay.
Now I
Why?
can give you an algorithm and like computational thing, but I think I will explain by an example. So remember that the L is a lower triangular matrix, right?
Yes.
So I'll just quickly try to write a lower triangular matrix. Allows me. Yes. So let's say, so that means everything above the diagonal has to be zero.
Hmm.
So this is zero, this is zero, this is zero.
Yeah.
Okay. And I'll put some random numbers here. 2, 4, 5, only 1, 2, 3. Okay.
Okay.
So, and let Y is basically Y1, Y2, Y3 kind of stuff.
Yes.
Matrix typing is terrible. Y1, sorry, 1, 2, Y3. And B also has B1, B2, B3. Then B3 might be more. So now while solving, so you see that when I multiply the first row times first column in L times Y is just 2 times Y1, right?
Yes.
So that's easy, right?
Yes.
So 2 times Y1 is B1.
So B1,
So
one is
Y, Y1 is just
B1 over 2.
half B1.
Okay, so I see what you're doing. Then you'll have just all of the system of equations, just one variable.
Yes. Y1 plus 4Y2 equals B2. Now remember that Y1 is already known. So only Y2 is unknown in this.
Yes.
So Y2 will be something. I'm not actually solving it. But at every step, you will have only one new variable introduced. Everything else is known.
Makes sense because of the lower
Makes
triangle.
sense?
Yeah.
Yes. So this only works because this is lower triangular.
Yeah.
So there are two important things. One is that from ux equals y, you can go back to x equals u transpose y. This works because the u is orthogonal.
Yeah.
Otherwise, we'll have a u inverse here. And again, inverse is very time consuming, as we discussed.
Right.
So that inverse to transpose that trick works because it's orthogonal. So that's the purpose of doing LU. This is actually like used in some places for solving equations.
Mhm.
This is one of the algorithms that many packages use.
Got it. Wait, sorry, what is this called?
LU decompositions.
How do you spell?
LU.
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 L LU.
Just the name. Yeah, yeah.
LU.
We remember it like that.
Okay, LU decomposition.
Okay.
Okay, cool. Okay, so this makes sense then, Sujay. So I'm glad. So but I would say we've pretty much covered the linear
We pretty
algebra.
much covered more than 80%
Yeah, that I would
of
need
what I wanted to cover.
especially for
Yes.
machine learning class then. Okay.
Yes.
Okay, great.
Okay. So should we move on?
Yes. If we're moving on to the, let me, can I maybe, I'm going to